radial transverse coordinates, polar coordinates. We have a position vector going from some observation point or some reference point. In this case it's A. And here the position vector, RB, locates point B. Okay, now RB vector is going to change its length and it's going to rotate. And we've defined unit vectors, one called UR, which is in the radial direction, which is in the direction of the position vector. We said that theta increases positive counterclockwise, so let's make our other perpendicular unit vector for our new coordinate system. UR rotated 90 degrees in the direction of increasing theta. So we'll rotate UR counterclockwise 90 degrees. Now we've got U theta. Okay? Two unit vectors perpendicular defining our new coordinate system. All right, so the position vector is RB in the UR direction. And as the point B moves, as that crane extends and rotates, those unit vectors are going to change. They're not going to get any longer or shorter, but they're going to rotate. So in lecture we drew an initial UR and U theta, and we showed them rotated through a very small d theta to UR final and U theta final. So basically UR initial and final, they're pretty much in the same direction. They're only separated by one of these little calculus style small angles d theta. I think most people understood, or at least remembered, how to draw delta UR, the change in the UR vector. It's UR final minus initial, which is minus initial plus final. So not a lot of people got that top hat question right about what direction it's in. Now I thought most people would get the next question right, which is what direction is the delta U theta vector in. I suspect most people were able to draw the delta U theta vector this way. But there seems to be a bit more of a subtle, confusing point here about what direction that's actually in. So let me start a new note here. All right, we are all used to I and j unit vectors, which are in the x, y directions. Okay, so we're used to x, y being fixed directions. And, if I was to draw this vector, and, if I woke you up in the middle of the night and said, I got this vector, don't ask me where I got it, I just got it. What direction is it in? I think you would probably say that that's in the negative y direction. Okay? And it wouldn't matter if I moved x and y around. Okay? All right? No matter which way, or no matter where I draw this little axis set, the y direction is still up and the x direction is still to the right. This little vector over here is still in the negative y direction. Okay. Now, x and y, or the unit vectors I and j that we associate with the x and y directions, they're not the be-all and end-all of coordinate frames. Okay? I could have any coordinate system I wanted. I could have it in any direction I wanted. Let's say, just to be cheeky, I define an axis set with two perpendicular directions, Tom and Bob. Okay? Now, if I draw this vector, what direction is it in? Say it out loud, risking the curious stares of passers-by. It's in the Tom direction. Okay? It's in the, positive Tom direction. So to get back to the point of today's lecture, let's say we have the crane, and we've got this fixed point A, and we've got point B on the end of that crane boom, and here's our vector, RB. Vector's changing. Suppose this is the path of the end of that crane. Now, it's not a circle. Point B is not moving in a circular path about A, it's just moving in some arbitrary path. So we walk up to our point B initially. What's the radial direction? By definition, the radial direction is the direction of the position vector. We ask ourselves, which way does theta increase? Let's make it counterclockwise. So, by definition, u theta is in the transverse direction, which is perpendicular to UR, but rotated 90 degrees counterclockwise, because theta increases positive counterclockwise. All right, so that's the UR direction. If I pick up this unit vector and I move it, that's the UR direction. That's the UR direction. I can draw this unit vector wherever I want. It doesn't change the fact that right now this is the UR direction. Okay, it's probably a bit more helpful to draw it there. Okay, now we're going to consider a short excursion of point B along this path. Now, I guess because I can, I'm going to pick up those unit vectors. I'm going to move them over there. So that's my initial unit vectors. All right. Now let's say we come along a little bit later and point B is in a final position in red, and now I've got a new RB vector. The radial direction by definition is always in the direction of that position vector. So now I've got UR that way. U theta is still UR rotated 90 degrees in the direction of increasing theta. UR initial in blue, final in red. Unit vector with length 1. But the vector changed. Okay? It rotated. Now, if we zoom in on this, I'm going to, in black, draw the change in UR. How did UR change? What's minus UR initial plus UR final? It's this black vector here. Okay. Now I'm going to do something similar to the whole Tom and Bob thought experiment. There's a whole lot of clutter here. I'm going to erase some things. I am going to erase that. Oops. I'm going to erase that. I'm even going to erase this. Okay, compare this to the Bob and Tom scenario. What direction is that little black vector in? Which, oh, by the way, is delta UR. It's in the U theta direction. It's in the positive U theta direction. U theta direction, sorry. Okay, so let's look at what happened to U theta. This was the U theta direction, and then the position vector rotated, and then we ended up with, oh, I didn't quite draw these very well. Anyway, the new U theta vector is rotated a little bit compared to the original one. What's delta U theta? It's minus initial plus final. It's this thing. Here's delta U theta. What direction is that in? Well, I'm going to reinstate my original UR vector. And I'm going to erase a bunch of stuff. Because all I care about, all I asked you today on Top Hat was, what's the direction of the delta U theta vector? It's in the minus radial direction. Okay. I don't know if that's going to clear things up or not. Hopefully this visualization will help. Okay. So with that, my hope is that we've established that delta UR is going to be in the U theta direction. Delta U theta is going to be in the negative UR direction. You know, the initial and final UR directions are basically the same, as I said before. The initial and final U theta directions, same as they were before. What's the magnitude of delta UR? It's approximately the arc length that was swept out by the UR vector as it rotated through this small angle. So delta UR's magnitude is approximately the arc length 1, which is the length of the vector, times d theta. the magnitude of delta u theta is approximately the length of the arc swept out by this u theta vector as it rotates. That arc length is 1 d theta. Okay, so we have the magnitudes of these delta u vectors, magnitudes d theta, and the directions are in the u theta direction for delta ur and the minus ur direction for delta u theta. If you're having trouble remembering that the radial direction is in the direction of the position vector, some people today said, when I think of radial, I think of radians, I think of angle, and I kind of get these ur and u theta directions mixed up. Think about a circle. Draw a radius. Okay? That's where the whole radial direction name comes from. We'll leave it there. We'll pick it up there in the next lecture. Thank you, and I hope this helped.